Page 20, so if you can open to page 20. And while we're opening to page 20, we'll take our look at the calendar. At this point of the semester, things get a little bit choppy because of days off. So last week we had advising day that didn't really affect us, but it was a day off if you had a Tuesday class. And then this past Monday was Veterans Day, so we haven't seen each other since Friday, which I know you're all very broken up about inside. And then next week is also a funny week because we have Thursday and Friday off for Thanksgiving. So it's kind of choppy at this point in the semester, but do whatever you can to try to keep your study schedule for your courses as regular as possible. However much time you are spending doing homework before, continue to try to do that even as there are days off that kind of break up the classes. So today, November 14th, we are on something called families of curves. Last class, we talked about optimization problems. That's the fancy word for saying make something as big as possible, find the maximum, and also find the minimum. And so we've spent time looking at local maxes and mins, and last class we looked at global maxes and mins, highest point anywhere on a closed interval, and the lowest point as well. Today we'll talk about families of curves, and the next few classes are also related to we're going to kind of start doing a lot of word problems, and that's what we have to look forward to in the next few classes. The next quiz is coming up on November 19th. Is that Monday? Must be Monday. All right, so quiz 7 is on Monday. Also on Monday is project number 6. That's when it's due. Okay, so hopefully we're working on project 6. And also on Monday, I will hand out project 7. If you want it early, it's sitting on the table. Questions on any of this? So just a reminder, today is officially a Monday schedule during the day. It won't affect us, and if you have physics, it won't affect that either. But if your afternoons are different on Monday, Wednesday, today is a Monday, okay? But if you have a Wednesday night class, that's what you go to tonight. No Monday night classes tonight. All right, so here on page 20, one other announcement. Because today is officially a Monday, the math club is going to meet today. So if you're interested in hanging out, and I think we're going to be solving Rubik's Cubes together, just right next door at noon today. You can bring your lunch. All right, so let's start with number 1. Chris, on page 20.
Formulas such as f of x equals a of x plus b times square root of x as a family of functions. A, B, C are called parameters. Family is a three-parameter.
Okay, and so we've got a whole lot of functions. What's the graph of every one of these functions called? Those are all parabolas, and there are lots of different kinds of parabolas. They can open up, they can open down, they can be real wide, they can be real thin, right? And they might have a max or they might have a min, and which ones of those attributes they have all depend on the values of A and B and C. And you guys probably have some stuff memorized, like which one of those letters determines whether it's an up parabola or a down parabola. It's A, right? And so you talk about how the x squared is the dominant term, and so it will eventually win. Using calculus, it turns out it's really easy to figure out that A is the thing that's going to dictate whether we're up or down. And the other day, Garrett mentioned the vertex formula. You guys remember? In terms of A, B, and C, what's the formula for the x coordinate of that vertex? So negative, thank you, negative b over 2a. So we'll actually go through the derivation again. We went through it real quick because Garrett called it out the other day. But it turns out it's really easy to figure out that formula using calculus. So let's jump to number 2. We'll go to Tiffany. Okay, so we've got that already. X equals negative b over 2a is a formula we'd memorized, but it turns out it's really easy to just figure it out using calculus. So what's our favorite thing to do in calculus now when we have a function? Is take a derivative. You guys are catching on here, like I said. Take a derivative is the answer to most questions for the rest of this semester. So take a derivative of that thing. A is a constant multiple. It's sitting there waiting. What's the derivative of x squared? 2x. So I'm going to put the 2 in the front. Plus, what's the derivative of bx? Is b, right? Just think of it like 7x. Derivative would be 7. What about the derivative of that plus c? That's 0. So here's our first derivative, and while we're in the derivative frame of mind, let's go ahead and find the second derivative. The level of difficulty gets ratcheted up when you have these constants sitting around. If it was just 7x plus 8, you guys would know the derivative like that, but sometimes it takes us a moment to just realize that we're looking at something just like 7x plus 8. What's the derivative of this? 2a. Good. Okay, so once we have a derivative, what's our favorite number to set it equal to? 0. We're looking for the turning points, the flat points. And so we set it equal to 0 and then solve. And solving that equation is a little bit harder than solving equations where you have numbers in them, but it's the same process. Subtract the b and then divide by the 2a, and we get our old friend. X is negative b over 2a. Of course, that's the only flat point on the parabola. It's the thing called the vertex. All right, and now that we've got that, let's go ahead and do our sign test. I'm going to label this sign test with an F prime. And what number goes on the sign test? It's the negative b over 2a. That's our critical number, right? So we put that on the sign test. But now things get really tricky. And again, we're at like a different level of generalization here. B and A are constants, and we really don't know anything about them other than the fact that they are constants. So how do we figure out what the sign is? Well, let's see. Suppose that we pick a number that's to the right. Okay, now I don't know what's to the right of negative b over 2a. Maybe 100 is big enough if it's not try a million or a billion, but we could eventually find some number that's bigger there. So let's go ahead and plug in some really enormous number right in here. So x is some enormous positive number, right? If I keep going to the right, eventually I'll find something bigger than that number. So I plug in some enormous positive number. Now 2 times a times x, is that positive or is that negative? Is it positive or negative? X is some enormous positive number. It depends, right? We can't say anymore definitively whether that's a positive or negative thing. It depends on the sign of A. Okay, so we now have 2 sign tests. So in the first one, I'm going to assume A is a positive number. And in the second one, I'm going to assume A is a negative number. And I didn't know that I was going to split that into 2 cases until I started doing my sign test. Until I recognized that, oh gosh, plugging an enormous positive number in there, I can't tell whether it's going to be positive or negative. It depends. And that's your key, that we're going to split this into different cases. All right, so in the first case, we're assuming that A is bigger than 0. So we're looking at that. So A is bigger than 0. What about 2 times A? Is that positive or negative? That's positive. And then we're multiplying it by this enormous positive number. And what kind of a thing do we get? It's positive. It's a really big positive, right? Now I'm adding B. Now B could be positive or negative as well, right? But this guy doesn't matter, because we assumed that we picked a number way, way, way bigger than this 0 that we've plugged in here. So presumably this enormous thing is going to dwarf whatever we got there. And if you don't buy it, if you believe that, oh, well, what if B is like a zillion, which by the way is not a real number, so don't use that number. But if B is like a zillion, well, then we wouldn't have picked 100 over here. We would have picked like 2 zillion or 5 zillion. Eventually something is bigger, all right? So it doesn't matter whether B is positive or negative. So we said this whole thing right here was a positive, plus I don't care about that guy, so the whole thing is positive. So out here we have positive numbers. Yes, we would pick X to be sufficiently big to counteract the smallness of A. It's a good question. All right. Okay, and then the next thing we're doing is plugging in a number that's out here. So like negative a zillion. So this guy is now negative a zillion. A is still positive. So what's the sign of this thing? That's a negative number. Plus, and again, I don't care how big this guy is, the B is not going to affect the negativeness of this thing. So to the left, we are negative. All right, and without going through that whole analysis again, if A is negative, what do you think happens to the signs we got? We're just going to reverse, right? And everything will change. So I'll go ahead and just fill them in the other order. Okay, so we've done everything we can here. We'll analyze it in just a moment, but let's jump for a second to the second derivative. Second derivative is 2a. There's no x's in there, which means if I try to set it equal to my favorite number, 0, it will never have any solutions, right? Setting the second derivative equal to 0, what are the answers called that we get out of there? If you get some x values when the second derivative is 0, those are inflection points, right? So what does this mean? It's never equal to 0, so it has no inflection points. Is that true? Yeah, for parabolas, they never change concavity, right? They're either always concave up or always concave down. And that's what this says. If A is positive, then second derivative is always positive. Agree? And if the second derivative is always positive, what's the concavity? Second is always up. If A is a positive number, second derivative is positive, and so F is always concave up. Does that agree with stuff you already knew about the parabola? If A is positive, we're an upwards opening parabola, which is always concave up. And you could write down the other sentence. If A is negative, I'm not going to write it down. But let's stick with the positive A's for a second. This sign test was the one that corresponded to the positive A's, bigger than 0. Until we get to the vertex, which is this critical number, what is the parabola doing? It's decreasing. And then we hit the critical number, and then we're increasing. And the whole time we are concave up. And that exactly describes what we know about parabolas when A is positive. Decreasing to the vertex, flat, and then increasing, concave up the whole time. So the point of this, I mean, we didn't learn anything new. You guys knew all this about the parabola anyway. But the point is that calculus affirms all these little formulas that we had you guys memorize in different algebra classes. And it affirms the things that we said were true. Oh, if A is positive, it opens up. And if A is negative, it opens down. But calculus gives us the way to like really precisely analyze the behavior of these functions. Calculus also allows us to answer questions like the one on the next page. We'll go to number 3 for Bubba. Okay, so a lot of stuff going on with this one. A lot of stuff going on. I'm going to draw a quick sketch. You don't need a sketch, but let's just see if we can get a handle on what we're after really. So we know we're going to hit the point 1, 4. So I'll put that point up here, 1, 4. And then I know that at x equals -1, what's the slope? Is 6. So I'm going to go to x equals -1. And I don't know where the point is. It could be really high or it could be really low. I don't know. But I know the slope is 6. So how about like here at -1, I'm going to say, okay, maybe if the point is down here at the bottom, then the slope would be like some steep +6, right? Or even if it's up here, the slope would be some steep +6, right? And in my mind, I'm imagining like a whole lot of really steep lines just going up and down. I don't know where -1 really is, but wherever it is, it's going to be some steep uphill thing. And then on the other side, we have at x equals 5, the slope is -2. So if I go out to 5, so let's say 5 is out here, what kind of a slope should we draw? Uphill or downhill? Downhill? Steeper or not as steep as the purple? Not as steep. Okay, so the slope is -2. If it's way up there, then, okay, so that's probably more of like a -1, but All right, so -2, and then slope down here, -2. So wherever it is, it's essentially going to look like one of those infinitely many green tangent lines. Okay, so I feel like I have a good sense. Is this parabola opening up or down? It feels like everything is pointing this parabola down, right? Do we kind of buy that? And I don't know exactly where it's supposed to go, but I'd imagine that I could maybe draw something and maybe it gets a little bit higher and then it comes down and then hits one of these guys. I don't know, something like that. But there's a lot of different parabolas to choose from, so let's pick the right one. So first we'll use this thing. The point 1,4 is on the parabola, so that means that f of 1 is 4. Agree? So let's go ahead and plug x equals 1 into this very generic quadratic formula. Quadratic function, I should say. So if I plug 1 in for all those x's, a times 1 squared, how much is that? That's a. So we get a plus b times 1, b plus c. And what is that supposed to equal? It's supposed to equal 4. So f of 1 is 4 gives us an equation. Bubba, is that all right? Okay. Questions on that? You plug in x equals 1, you get an equation. That equation isn't enough by itself, but it's some relationship that we'll end up using. Hopefully we'll have more info coming. And then we also talked about the slopes. So if I want to think about slopes of tangent lines, what calculus thing should I do? Take a derivative. So f prime of x, we've already seen the derivative for this guy. It's 2ax plus b. Should I set it equal to 0? No, there's nothing in this problem that says find the critical numbers. So don't set it equal to 0 just because, I mean, you can if you want to, but what's that? You could find a general formula for the vertex, the negative b over 2a, but there's, I don't know that we could use it, but we're going to use the data that we've got up there. So I'll use the purple point first. X is how much? -1. So 2 times a times -1. Oh, sorry. Yeah, that's right. 2 times a times -1 plus b. What is it supposed to equal? It's supposed to equal 6. So everybody see where those numbers came from. And if you see where those came from, you should be able to write the green equation. X is 5, the slope is -2. What's our equation here? So I'm going to write 2 times a times 5, yeah, but it does become 10a plus b. Are there any questions about those equations? All right, now you guys have lots of experience solving systems of equations. These are two linear equations with a and b in them. Maybe you add the equations together, maybe you solve one equation for b and plug it into the other. Right? You guys have done problems like this before, yes? We have some idea of techniques we would use to solve these equations? So you do something to find a and b, and then once you found a and b, how would you get c? So a and b in the original won't give it to us, but into the black equation at the top there, 4 equals, right? Okay, so some of us, I think, have already started the algebra. I'm not so interested in the algebra, so I'm just going to write the answers, and you can verify later on. But I got a is -2/3, b is 14/3, and c is 0. So you can double check that later. Okay, any questions on that? The idea with problems like this is that, I mean, you can't practice to the point where you will have seen every single type of problem I might throw at you on a quiz or a test. But that's not the idea. The idea is that you can take the givens that I provide and just reason your way through. Okay, I know the derivative is involved somehow. How do I use the derivative? okay, the 0.14 is on the curve. How do I use that? And use all of the tools that we've developed to come up with some equations, and then hopefully you have the ability to solve those equations. All right? So there's a lot of variations on the theme here, but the big picture is that you should be able to take the given information and somehow translate it into calculus speak, into derivatives, into equations. All right, let's take a look at number 4. Number 4, and we'll go to the back to Sam. Okay, so this is going to be more complex, but can you guys take a look at the yellow function compared to the green function? So which one looks easier to deal with? Yellow. But if we understand everything there is to know about yellow, which we don't know anything about it yet, but once we do, would you guys agree that to get from yellow to green, it's just a horizontal shift? If x becomes x minus a, then we're just shifting, left or right, depending on what a is. So we're not going to deal with the a version first. We'll deal with the green. All right, and can we go to Todd for the warning? Okay. All right, so let's give it a shot. What's our favorite calculus thing to do? Take a derivative. So let's take a derivative here. This is e to some stuff. What's the rule for e to the stuff? E to the stuff times the derivative of the stuff. Now the derivative of negative x squared over b, you could use the quotient rule, but you do not need to. I'll just put this little scratch work on the side here. Negative x squared over b, for me, becomes a negative 1 over b times x squared. So first, do we believe those are equal? And if you wanted to see the, over 1, and then you just multiply across for the fractions. And that translation is something that I do immediately. And now that negative 1 over b is a constant multiple. It's just sitting here waiting for you to take a derivative of x squared. So what's the derivative here? So this becomes a 2x with the negative 1 over b just sitting in the front. And so the derivative is negative 2x over b. So we'll put that over here. Negative 2x over b. Okay, and are there questions on that? You can use the quotient rule. Really the only way to go wrong is to treat b like a variable. Right? We're not, like the derivative of b is not 1. What's the derivative of b? It's 0. Okay, so if you're using the quotient rule, that's the only thing to worry about. B is a constant, so its derivative is 0. Okay, and while we're here doing derivatives, let's go ahead and do one more. F double prime of x. Raise your hand once you see the bad news with taking f double prime. Why is it going to be bigger? What rule are we using? Product rule, right? This is the bad news. And that reminds me of a question Garrett asked way back when. He says, for polynomials, when you take derivatives, they get nicer, right? The degree goes down by 1. But we were then coming up with formulas where the derivatives get worse. And I think I said something like, generally derivatives get worse, and polynomials are the exception rather than the rule. All of a sudden, we have a product rule when we didn't have one the first time through. Okay, so we'll use the product rule. First times derivative of the second. Derivative of negative 2x over b. I'm hoping you guys can do something like we did over here on the side in black. Try to avoid using the quotient rule for this derivative. Does anybody see the derivative of negative 2x over b? What is it? One vote for this. Other votes for that? That's it. That's the derivative. And in your mind, just take that x and pluck it off and put it to the side. Then it's just a constant times x. Derivative is just the constant. Okay, plus we were in the middle of the product rule. Plus the second, negative 2x over b, times the derivative of the first. We can be really clever here because the derivative of the first is the same as the derivative of the original problem, right? And so we wrote out in blue what the derivative of the original was. So that whole thing in blue is about to get copied down over here. Does everybody see that little time saver we applied? Yeah, you could do that. Yeah, the negative 2x over b appears twice there. So you could merge these guys together. Okay, so before we do anything with that, we're going to want to clean it up. And I'm going to do the algebra here kind of quick because I really want to focus our time on the calculus. So you can check the algebra later on. We're going to factor some stuff out. We're going to factor out an e to the negative x squared over b. And we're also going to factor out a negative 2 over b. So all that stuff is going to come out of both terms here. Okay, if I factor e to the negative x squared over b and negative 2 over b out of this red thing, what's left? 1. We factored all of it out, so all we have left is the placeholder of 1. Okay, that's good. Now we're going to factor that same stuff out of here. Here's where things get a little bit hairy. So the e to the negative x squared over b is outside, so we don't need that anymore. I do want to pull out a negative 2 over b, which I see here. So that guy is outside. So what's left over is everything that isn't checked yet. So there's a solitary x and a negative 2x over b. You see that? And pulling off that negative 2 over b is the same technique that we used over here in black. It's just thinking of the x as being off to the side. The negative 2 over b comes out, x is still there. So what's left over, I think, is a minus. There's a 2. There's an x. There's a b on the bottom. What am I missing? It's x squared. That purple x tacks on to the other x. So double check the algebra later. That is not our focus. We're focusing on the calculus. So now that we've got this simplified as much as possible, we can do the calculus. There were actually 2 negative signs. There was this one and this one. So one of them came out, yes. Yeah, I got to be real careful with the signs. Okay, so we've got our 2 derivatives. What do we do with our derivatives once we have them? Set them equal to what? 0. Okay, so let's set them equal to 0. We'll do them separately. So this one equals 0. Well, I've got 2 factors. I've got the e part, and I've got the negative 2x over b. What values of x make e equal to 0? There aren't any, right? E equals 0 never happens. You guys know the e to the x curve never hits the x-axis. So that part doesn't contribute anything. So we get to focus, which is really nice because you can ignore it. That was the complicated part. Doesn't matter. We can focus on the second term. Negative 2x over b. What value of x makes that thing equal to 0? Is 0 itself. The only way to make a fraction 0 is which part? Is the numerator. The only way to make 2x equal to 0 is if x is 0. So x equals 0 has a name. What is it called? It's our critical number. Okay, and now that we have our critical number, I'm running out of space here. I'm going to send this down here. Now that we've got our critical number, we're going to go ahead and do our sign test. What number goes on our sign test? 0, the only critical number we found. And so first thing we'll do is pick a number that's way out here to the right, something like x equals 1,000,000, positive 1,000,000. If I plug x equals positive 1,000,000 into this right here, what can you tell me about the whole value of this? X is positive 1,000,000. Is that a positive thing or a negative thing? Maybe it's hard to say because we don't know anything about b. But again, think about e to the x, just e to the x. Swooping up never hits the x-axis, which means that it is also never below the x-axis. So what's true about e to any number? Always what kind of a thing? Always positive. It will if b is a positive number. But all I care about is the sign of it. So we don't even need to get into anything complicated about that exponent. E to any number is positive. So that whole red circled thing is going to be positive for both sides of 0. Doesn't matter what kind of a number I plug in. So don't get lost in the details. E to anything is positive. So this guy is always positive. Okay, so now we come to the second term. So I'll circle this one also in red. I'm plugging in x is 1,000,000. So I have negative 2,000,000 over b. Is that positive or is that negative? It depends on b. Okay. At this point, we recognize, all right, we got two of these guys. Really depends on the sign of b. So for the first one, I'll assume that b is a positive number. And for the second one, I'll assume b is a negative number. Okay. So again, I'm going to figure out the sign of this fraction when x is positive 1,000,000. If b is positive, I'm in my top sign test. What can you tell me about the sign of this thing here? It's a negative. Everybody see that? If b is positive and x is 1,000,000, that fraction is negative. So out here, we get negative numbers. Stay with the positive b, but now make x negative 1,000,000. And what happens to that fraction? Now it's positive. And now in the other sign test, if b is negative, what do you think happens to the answers we just got? They just reverse. I mean, if something is dependent on b, then it sure feels like things are just going to reverse from what they were. Okay, so if b is positive, this function is first increasing and then decreasing, going up, coming down. If b is negative, it's the other way, going down, then going up. Okay, let's move on. We've gotten everything we can out of the first derivative. We'll move on to the second derivative. So we're here in purple. Again, our favorite thing to do with derivatives is set them equal to 0. All right, this thing here has 3 factors. This thing circled in green, this other thing circled in green, and then everything in the brackets. 3 things multiplied together. We're trying to make them each equal to 0 individually. You see why factoring is so useful, is that you can make each term equal to 0 and they're completely independent. B is a constant. What do you think about negative 2 over b? Never 0. Agree? B is just some constant. What do you think about e to the negative x squared over b? It's never 0. Right? Saw that up above. So the only thing we have to focus on is in the brackets. And this is why you guys took years and years of algebra before you could take this class, so that you could do this kind of thing and then say, oh, all I have to do is worry about the thing in the brackets. So we'll solve the equation equal to 0 in the bracket. So let's write it here. 1 minus 2x squared over b is equal to 0. How about we move there are several different ways to solve this. I'm going to move the fraction to the right-hand side by adding. So I get 1 equals 2x squared over b. And then what should we do? Multiply by b, cross multiply if you prefer. So we get b is 2x squared. Again, the focus is to solve for x. It's tougher because we've got other constants floating around. Take the square root. Not yet. First divide by 2. And then we take the square root, and we get x is the square root of b over 2. What am I missing? Plus or minus. If you take the square root, you need to put in that plus or minus. Okay, so now that we've got those guys, what are they called? Places where the second derivative is 0. Inflection points. I'm going to just say one little thing. I'm going to say that these guys here are candidates for points of inflection, POI. They're candidates for points of inflection. To actually become a point of inflection, the concavity needs to change. So if it went from concave up and then it stayed concave up, then you wouldn't have a point of inflection. So those guys are just candidates. All right, and let's go ahead and do our sign test. This is going to be tough. I'm going to put those two numbers on my sign test. Negative root b over 2 is definitely smaller than positive root b over 2. And this sign test is applied to f double prime. Okay, so let's see if we can get f double prime on the screen. All right, that's about as good as we can do. We're using this version of f double prime that's factored. Let's go ahead and plug in x is something really huge, way bigger than root b over 2, whatever that is. So x is a bazillion. Positive. Negative 2 over b. Is that positive or is that negative? Oh, it depends on b. Okay, there's good news about to happen. If b is positive, then we can figure stuff out. If b is negative, then what do you guys think about this square root if b is negative? Then it's imaginary. Ah, okay. So if b is negative, then there are no points of inflection. The analysis is done for that side. They don't need to go through a duplicate sign test. If b is negative, then the solutions there are not real numbers. So we've got no points of inflection. So the only way we're getting to do our sign test is if b is positive. All right, we've already handled the other case. Okay, so assume b is positive. We're picking some number way out here to the right. X is a billion. So negative 2 over b, if b is positive, what kind of a thing is that? That's a negative number there. E to anything, always positive. And now we plug in x equals a billion in here. What do you think? 1 minus, and still b is a positive number. It's going to be negative. I'm hoping that you can kind of reason your way through. You're doing 1 and you're subtracting, and all of these things are positive. So you're subtracting some enormous positive number. So this whole thing is a negative. Joe. Yes. No, when you want the second derivative to be undefined, what we're really saying is that it has a denominator that's equal to 0. Yeah, so we're not looking for square roots of negatives. We're looking for denominators of 0. Good question. Okay, so what did we say the whole thing was here? A positive when we multiply them all through. Okay, if we plug in, let's jump to the far left. If we plug in like negative a billion for x, what about the first two signs? They're the same. There's no x's that we have to worry about for the first two. If x is negative a billion, don't forget you're squaring it in here. What's going to happen to that sign? It's going to be exactly the same. You see it? X equals negative a billion will be exactly the same because it's getting squared. So out there, also positive. There is one concrete specific number that we can pick in between here. What number is definitely in there? 0 is definitely in there. So let's pick 0. The sign of the first two things, same. Doesn't matter what x was. When x is 0, how much is in the purple brackets? 1. All right. Positive. So what's the sign of the whole thing? Negative. So you guys are going to say up or down. On the far left, are we concave up or down? Second derivative is positive, concave up. Then it becomes concave down, then it becomes concave up. Okay. Last thing, and then we're going to look at Sketchpad to see how all this analysis ties together to a real nice picture. The last thing is going all the way back to the original. And suppose that I wanted to think about end behavior for this guy right here. I'm going to assume that b is bigger than 0. I just want to focus on that case. So end behavior. If x is 1,000,000, what can you guys tell me about e to the negative 1,000,000 squared over some positive number? E to the negative 1,000,000 is very close to what? It's very close to 0. E to the negative 1,000,000. You think about your favorite e to the x curve. If you send x to negative 1,000,000, we're getting closer and closer to 0. We'll be pretty much right on the x-axis. So if x is positive 1,000,000, we go to 0. What if you plug in x is negative 1,000,000? It's still 0 because we're still squaring. It's going to look the same on both sides. So the end behavior is that limit as x goes to either infinity or negative infinity of this function is 0. We're going to get close to the x-axis on both sides. All right, so we've done tons of analysis, lots of work. Let's see if we can put it together on one nice pretty picture. There's our nice pretty picture. At the moment, the b value is positive 1. The a value is 0. We're not going to worry about that for right now. And I'm looking at this. What did we say? You guys have the pictures and all the sign tests in front of you. At the far left is concave what? Up. It is, until that yellow point. That yellow point is the square root of b over 2, a negative in front of it. And then it becomes in between the two yellows. What does it become? Concave down. And then after the last yellow, it becomes concave up. Now look at the first derivative information. What was the critical number? 0. We had two cases. Here b is a positive. When b was positive, the sign to the left of 0 was positive. It went positive, meaning increasing, until we get to 0 where it's flat, right at the top there, and then decreasing. And it looks like the bell-shaped curve that you guys maybe have seen before. And I can take b and I can change it. I can make b bigger. And so these square roots of b over 2 become bigger, but it still behaves the same exact way. And then if we take b and make it negative, oh, well, one small thing we can do. Remember we had said a is just horizontal shifts, right? So I can just take a, and the analysis is exactly the same, just shift it left and right. So that part's not very interesting. And then what happens when b becomes a negative number? Yeah, somehow it's going to flop over. What happens to the point of inflections when b is negative? We got imaginaries. Yeah, they don't exist. There's somehow it has 2 points of inflection, and then in the blink of an eye, it's going to have none. And also, what was true about the first derivative there? It was a negative until we got to the 0, and then it was positive. So we're looking for something that's going to be decreasing and then increasing. So something quite dramatic happens as we change, and it's like there's nothing smooth about that transition. In most cases, I think that things are smooth, but I don't think this one is. The 2 points of inflection completely vanish. This guy is always concave what? Up, and it goes decreasing until the 0 and then increasing. Okay. I mean, it looks like a parabola. It's not, because it's not just an x squared, but it behaves like a parabola in that way, yeah. And that's it. And you can see here the undefined parts. These were the points of inflection, and all of a sudden they become imaginary numbers. Okay, so here is the plan. We have 24 minutes or so. On the next page, there are 2 group problems. And before we, so last thing to say about today, during the fall semester every year, the students are asked to evaluate every full-time teacher here at GCC. And so in about 10 minutes or so, one of my colleagues is going to come in and administer a survey to you guys. There's information that you're going to write on that survey up here. I'm not allowed to be in the room when you complete the survey. So all I'll say is this. There's 2 parts. There's the fill in the bubble, like a strongly agree, disagree kind of thing. That's easy, that's quick, and you can zip through that. Super. There's also an optional comments page. And I'm really hoping that you guys will take a few minutes of your time today in our class to give me some feedback. I think that a lot of the improvements that I make from semester to semester come from feedback of students just like you guys. You don't need to write anything down. I know some people don't like to write sentences. Look, there's not a spelling test. There's no grammar to worry about. Just get sentence fragments up here, just anything at all. Just get some thoughts on the page. I really do think that I make a lot of changes from semester to semester based on this moment right here. I think I've given you guys a lot of feedback throughout the course of the term. I'm hoping that you guys will give me some feedback today. Last thing to say, I don't get to see these until like February, way after grades are due. So don't try to butter me up and hope that your grade is going to improve. And also don't fear repercussions if you write some constructive criticism here. Nothing that you write is going to affect your grade, okay? So just be honest. That's all that I'm looking for, all right? All right, so so she's going to come at like 9:35. You're not going to take 15 minutes to do all of this. So as soon as you finish the survey stuff, you just keep working on the group work with your neighbors. So let's see how far we can get here, and she'll be here in just a few minutes.